Well, now let's have a little bit of fun and see how capacitors combine in series and parallel configurations, what the difference is. You may have some recollection about how resistors add in series and parallel. It's okay if you don't, we'll discuss that later. But here we have two capacitors in series, and series just means that any current going through, I say through loosely, has to go through the other one. Through one, it goes through the other one. So, in other words, there's only one path for the current to flow, and that's through all the components in series. Now we have a voltage across A and B, which is VAB. So VAB is just the terminal voltage from A to B across the two capacitors. The charge on Q1 equals the charge on Q2 is equal to Q. And that's going to require a little bit of explanation, but it's not too difficult to understand. In series, any charge that's on one is on the other. Because here's positive charge Q that's deposited onto it by flowing from A onto the capacitor. Now when that happens, ultimately it's going to push off negative Q off of this side and back around to the power supply or the battery, whatever it is. So charge coming into the circuit, into the top part of this capacitor, leaves here. The total amount of that charge is Q. Everything that happens inside between those two extremes really doesn't matter, because the inner plates, you can look at this in isolation, spatially and physically, these are, well, really the same thing there. These are isolated. In other words, they're not electrically connected to the rest of the circuit. So they're isolated. The negative of C1, that would be right here, as this positive charge pushes off positives from this plate, those positives make this side negative. It shoves those positives onto the first side of C2. So that negative and positive here is not additional charge. It's charge that was on here that got shoved off here. But if you look at this electrically isolated part, there's been no net change in charge in the circuit. It's just shifted around a little bit. The only change in charge is plus Q coming in here, negative Q coming off of here, plus Q coming off here making that negative and going back to the circuit. That's it. Alright, so we have V1 and we have V2. The voltage across capacitor 1 and capacitor 2. Well, voltage is charge over capacitance. Remember, capacity is Q over V. And V2 is Q over C2. Recognizing now that Q's are the same for both of them. So VAB is equal to the addition of those two voltages, V1 plus V2, so it's Q over C1 plus Q over C2. Divide this by Q, and we get 1 over C1 plus 1 over C2. That's V over Q. So what we're trying to do is figure out the effective equivalent capacitance of these two capacitors. So let's draw it. Here it is. We have a voltage across a capacitor, plus Q and minus Q, equivalently. So what is the C equivalent of those two? Well, it's Q over V. The Q that we're talking about that hasn't changed along here. All these Q's are the same magnitude. And now we're going to divide it by the voltage, which is given to us by this expression here. So to make this simpler, we have 1 over, we have V over Q. So let's go 1 over C equivalent is V over Q. V over Q is 1 over C1 plus 1 over C2. So let's finish the problem and see what that is. So generalizing, we have that 1 over C equivalent is equal to the sum of all the 1 over C's that are in series with each other. Now we can see from this that if we have more than one capacitor, 1 over C equivalent just gets bigger and bigger and bigger as we add these. Therefore, C equivalent gets smaller and smaller and smaller. And it immediately follows then that C equivalent is smaller than the very smallest capacitor that's in series, based on how the math works out there. So the equivalent capacity in a series circuit is always less. It keeps going down, 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 and it's going to be less than the smallest capacitor that's in series. So there's the formula for capacitors in series, and now let's consider the parallel situation. Here they are in parallel. We have two capacitors in parallel, which can be seen by the fact that to get current from one terminal to the other, it has one path to go, and it's got a second path to travel for current to flow around. So these two paths are somewhat independent of each other. Okay, so you can have one, you can have charge flowing across one and then across the other one. Now, Q1 is C1 times V. Q is equal to CV. C is equal to Q over V, remember? All right. And Q2 is equal to C2V. So those are the charges on the given capacitors. Now, because each individual one can have a charge that flows around the circuit, on here, off of here, and around, they add together. Q totals Q1 plus Q2. So that is C1V plus C2V. Now I dropped it over here, but notice there's no subscript on the V. Why is that? Here's V. Okay, potential difference across here. The potential across this capacitor and this capacitor have to be the same. Why? Because these are conductors, conducting wires connecting this. There can't be any potential change across a conductor. So whatever the potential is here, it's the same thing here. Whatever the potential is here, it's the same thing here. Voila. So V factors out, and Q total is V times C1 plus C2. Let's divide Q total now by V. When we do that, we get C1 plus C2. Well, Q over V is our definition of capacitance. So let's now express the equivalent capacitance of capacitors in parallel, and that's C1 plus C2 in this case, the equivalent capacity. So extending that, C equivalent is the sum of all the individual capacitors connected in parallel. It's like putting a whole bunch of buckets together and filling them all up individually. You have a combined capacitance equal to the sum of all of them. Now, if you have any recollection of how resistors work, we'll get to that later, but this is exactly the opposite. When you have parallel resistors, the total resistance is less than any of the individual resistors. In series, they add together. So that'll come later, but there's a basic overview of how capacitors add and combine in circuits. Let's do an example now. Let's now have a little fun and reduce this set of capacitors down to an equivalent single capacitor from the point of view of between terminals A and B. Now, external to A and B is a circuit or a battery or a power supply or a signal or some other stuff. It doesn't really matter. But it's important to realize that between A and B, what does this set of capacitors look like? That's what we're asking. So to do that, we combine them, series and parallel combinations, and we start with the most internested capacitors that we can combine, and hopefully that reveals itself to you as being the 12 and the 6. And that they're in series, because any charge going this way has to go across both to go to the rest of the circuit. So they're in series, so 1 over C is 1 over 6 plus 1 over 12. That's 2 6 plus 2 12s plus 1 12 is 3 12s. 12 thirds is 4. So C is equal to 4. So let's redraw this. Here it is. These two became a 4. Now these three together are in parallel. 3 separate paths for charge to flow. So you just add them. You get 18. So this simplifies down to an 18 microfarad capacitor and a 9 microfarad. They are in series. So 1 over C is 1 over 18 plus 1 over 9. That's 3/18 for 1 over C. 18 over 3 is 6 microfarads, which is the equivalent capacitance of this set of 5 capacitors. Wasn't that fun?